Welcome to the Electrical and Electronic Engineering Lecture Series. The anchor person is Professor Michael Sindinechi, and our topic today is Module 051, which is on Field Effect Transistors. We'll be looking at the principles, types, and applications. Please do well to join me in my engineering lecture series subscribing to my YouTube channel at https://youtube.com/@ndinechimichaelc. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can also listen to my lectures on Schottky diodes, Schmitt triggers, and Zener diodes using the links provided. These lectures will assist you to understand this topic, field effect transistors, better, as the field effect transistors make use of some principles of the Schottky diodes and the Zener diodes for their operations. You can also visit Ebony Educational Consult website for more engineering lectures which are free at www.ebonyeducationalconsult.com. Now, back to our lectures. Our topic today, as we said, is the field effect transistors, otherwise known as the FET. And it is a semiconductor device which can perform many of the functions of the bipolar junction transistors, but operates in a different way. In our previous lectures, we've talked about bipolar junction transistors, and we know exactly what they mean. But in case you are not conversant with the BJTs, you can, check up my lecture on semiconductor transistors by getting to my channel, the Engineering Lecture Series. This FET operation depends on the control of current by an electric field. Like the bipolar junction transistors, the FET has three terminals called the source, the drain, and the gate. The gate acts as the control terminal, and any voltage applied between the gate and the source controls the flow of current between the source and the drain. Therefore, FETs are voltage controlled rather than current controlled devices like the BJT. It is important for you to note this because it is a very important demarcation between FETs and the BJTs, because FET is voltage controlled while BJTs are current control devices. As we go on in this lecture, you will understand what made this to be voltage control and the other to be current control. In FETs, the current is virtually zero, and this gives it very high impedance of the order of 10 raised to power 12 ohms. Now, please join us in this lecture. In the next few slides, we'll be talking about the importance of a device having high input impedance and what it implies. It is very important that as a student of electronic engineering, that you understand this very well, because it is something you will be meeting from time to time that a device has high input impedance, and by just hearing that, you should know the implications of that statement. In the next 2 or 3 slides, we'll be talking about it in more details. Now, this type of transistors, that is the FETs, is highly used in the fabrication of very large-scale integrated circuits, such as microprocessors and memory devices. As we go on also, we will see why they are highly used in these devices. Of course, all of us are conversant with the works of microprocessors and memory devices in our digital systems. If you are not conversant with it, get to my engineering lecture series channel, you will see a lecture dedicated to computer architecture. You will know the importance of microprocessors and memory devices there. The FETs are known as unipolar transistors since current flow is by the carriers of one polarity, that is, the majority carriers. And we say at this point that you should recall that in the bipolar junction transistor, current flow is by both majority and minority carriers. Because in BJT, the current flow is by majority and minority carriers, we say that it is a bipolar device. And in field effect transistors, current flow is just by only majority carriers. Then we say that it is a unipolar device. What are the types of these field effect transistors in existence? And we say there are 3 basic types of field effect transistors, namely the junction field effect transistors known as the JFET, the metal oxide semiconductor field effect transistors known as the MOSFET. This is more common, you will be meeting in your digital systems, in most of the electronics textbooks you will be reading. And the third one is the metal semiconductor field effect transistor, the MOSFET. We will see the differences between them as we go down. Each of these FETs is available either as N-channel or P-channel field effect transistor with their symbols shown in Fig 1. Now, if you look at Fig 1A, which we call the N-channel junction field effect transistor, B is the P-channel junction field effect transistors. I want you to look closely at Fig 1A and Fig 1B and convince yourself that you know the difference, because that is the symbol you will be seeing in your circuit diagrams. The difference in the symbol is that for the N-channel JFET, the arrow at the gate is pointing to the junction, while in the P-channel field effect transistor, the arrow of the gate is pointing out of the junction. Likewise, in the MOSFET symbol, the arrow of the body for the N-channel is pointing towards the junction, while that of the P-channel is pointing out of the junction, that is indicating the body of the device. Now, the MOSFET is just almost the same as the MOSFET, except that in the electrical construction, so the diagram is not different from that of the MOSFET. Now, let's quickly look at the JFET. We say that the JFET junction field effect transistor consists of a piece of high resistive silicon that constitutes a channel for the flow of majority carriers. The magnitude of this current is controlled by a voltage applied to the gate, which is a PN junction formed along the channel. When we were treating our diodes, we have seen what a PN junction is. That is why at the beginning we say that looking at our lectures on Zener diode, for instance, we assist you to understand this better. The field effect transistor gate source junction is operated in the reverse bias region, thereby making the gate current to be practically equal to 0. We have seen in our previous lecture what a reverse bias region means. That at that point, the current is always 0 until it gets to the breakdown point, the knee voltage, where the device breaks down and currents are allowed to flow uncontrollably. Next is the MOSFET, which we say is the metallic oxide semiconductor field effect transistor, and its operation depends on the fact that it is not necessary to form a semiconductor junction on the channel of an FET in order to achieve gate control of the channel current. Instead, the gate electrode is a metallic region separated from the conducting channel by a thin silicon dioxide layer. Hence, you have the name metallic oxide semiconductor, MOS. Since the gate is electrically insulated from the source drain current, its voltage polarity may go either positive or negative without gate current flowing. We repeat that. Since the gate is electrically insulated from the source drain circuit, its voltage polarity may go either positive or negative without gate current flowing. So if you go back and look at the circuit symbol, you see that for the metallic oxide semiconductor symbol, the gate is not touching the junction there, where you have the drain and the source. So we say that it is electrically insulated. So it doesn't matter the polarity of the voltage passing through the gate. It doesn't affect what happens in the drain source. Now, this allows for the construction of two types of MOSFET. The first one is the enhancement type. This enhancement type conducts only when forward biased and is cut off at 0 volts between gate and source. And the second one is the depletion type, which conducts in both forward and reverse directions and is cut off only when the gate source is reverse biased by several volts. Like we said, we have looked at this forward biasing, reverse biasing, and what they really mean when we talked about our Zener diodes. That is why it is important that you understand the workings of the Zener diode before looking at the field effect transistors. Now, the third one is the MOSFET, which is metal semiconductor field effect transistor. And this is a unipolar semiconductor device that uses metal semiconductor Schottky junction for its gate. In our past lecture, module 049, we have dedicated it to talking about Schottky diodes and Schottky junction. So this MOSFET applies this Schottky junction principle for its gate. This distinguishes it from JFET and MOSFET. It is popular for high-frequency applications like microwave amplifiers in your cell phones and in radar technologies. MOSFETs offer advantages such as high switching speeds and high operating frequencies due to the use of semiconductor materials like gallium arsenide or silicon carbide. They control current flow through a conductive channel by varying the gate voltage, which alters the depletion region at the Schottky junction. We have under field effect transistors some parameters we need to commit to memory that will help us to understand more the working principles of FETs. And these major parameters include the I subscript DSS, which is drain current with gate shorted to source, V subscript GS off, meaning gate source cutoff voltage, then IGSS, I subscript GSS, which means gate source current will drain shorted to source. VV subscript GSS, which is gate source breakdown voltage will drain shorted to source. G subscript FS, which is common source forward transconductance. C subscript GS, which is gate source capacitance. C subscript GD, which means gate drain capacitance. And R subscript DS, which means drain source resistance. Now, let's see how these terms are used effectively in the FET equations. Say that some useful FET equations can be derived from typical transfer characteristics curve for an FET showing ID, which is the drain current, versus the V subscript GS, which is the gate source voltage. As shown in Fig 2. Now, if you look at this Fig 2, it's a plot that starts from, that's done at the saturation point where the gate source voltage is cut off and starts to pass current. That is where we have the V subscript GS off. Now, you see the sharp rise in ID as the voltage VGS, that is gate source voltage, increases. So if you look at this, we say that this curve represents the case where the device is in the saturation region and follows the square law and may be described by the following equations. Now, before we get to the equations, it is important for us to know what this square law means. For instance, if we look at equation 1, if in that equation 1, if K is 1 and V subscript GS, that is gate source voltage, is 5, for instance, and the cutoff voltage, gate source voltage, is 4, you can see that 5 minus 4, which is 1 squared, will give you 1. But immediately that changes by, slightly, and VGS becomes 6, while VGS off is 4. It becomes difference 2. 2 raised to power 2 will be 4. So you see that a small change, which is just 1 unit change, from 5 to 6 of VGS will increase the current from 1 to 4, showing that there will be a sharp rise. That is the meaning of the square law, that the slightest change gives a very large differential output. So we say that this ID follows the square law. That is, the drain current increases sharply as a small change in the applied gate to source voltage is done. That is at the saturation region. That is what is meant by square law, and that is what is represented by equation 1. And we say now, note that when VGS is equal to 0, ID is equal to I subscript DSS. That is, the drain current is equal to the drain current with gate shorted to source. Therefore, if you substitute that into equation 1, you can get the value of K, which is a multiplying constant with which the current rises sharply. So if we substitute that VGS equals 0 and ID equal to IDDS into equation 1, we get the value of K to be K equals I subscript DSS over VGS at cutoff squared. We call that equation 2 for easy remembrance. Now, if we take that equation 2 back to equation 1 to get the value of K and to, so that K can be eliminated because K is unknown, then we have equation 3, which says that the drain current is equal to the drain current with gate shorted to source, or into 1 minus the gate source voltage all over gate source voltage or at cutoff, which we call equation 3. So we have succeeded in eliminating the unknown, which is K. So this drain current of a JFET operating in the region below the pinch-off is given by the equation. If we manipulate that equation 3 given by the equation I equals I subscript DSS, or into VGS over VGS of all raised to power half. Then we call that equation 4. We now come down to the transconductance G subscript Fs, which is a measure of the effect of gate voltage on drain current, and is given as G subscript Fs, which is equal to change in ID over change in VGS. Equation 5. From that equation for ID, that is our equation 4, we have that G subscript Fs is equal to change in ID over change in VGS, that is the ID over the VGS, which is equal to 2 IDSS over VGS at cutoff, all into 1 minus VGS over VGS at cutoff. Just to differentiate that equation 4, if you do that, that is what you get, will be what is stated in equation 6. So it's just the differential of equation 4. So if we now call this G subscript F S naught, the value of the transconductance at VGS equal to 0, then we substitute again. That will give us equation 7. So equation 7 gives the value of the transconductance at VGS equals 0. Then you can now use it to know what happens if your conductance varies from time to time. And it is a function of the VGS, which is the voltage or gate source voltage. That is the voltage you are applying, and the gate source cutoff voltage. Transconductance is a function of that, and the relationship is as shown in equation 7. So you see that with all these equations, you can determine what is happening, but the important thing for you to note is that the current flow, which is the important thing to us, is taking the square law. In other words, a small change in the applied voltage, that is the gate voltage, will give a sharp rise in current flow. What are the general characteristics of these field effect transistors that you will commit to mind, so that anytime you are talking about field effect transistors, you get to know this, and if you remember them, it will help you to keep remembering what field effect transistors are all about. The first one is that they have high input impedance ranging from 10 raised to power 6 to 10 raised to power 12. Shortly, we will still see the importance of this high input impedance. The second characteristic is that they are voltage-controlled devices. We made it clear that they are different from the BJTs because they are voltage-controlled devices, and we have seen that the gate source voltage affects the current that flows between the source and the drain. And we made it clear also that they are isolated, electrically isolated, thereby the polarity of the voltage does not really matter. So, say, by being voltage controlled, they require negligible input current. You can see that, big characteristics. Then that they are unipolar device, that the conduction is only by majority carriers. So we say they are unipolar devices and their conduction is done by only majority carriers. Then they are low noise devices compared to BJTs, bipolar junction transistors. And finally, they have very good thermal stability, which is far better than that of the BJTs. By thermal stability, we mean if the temperature of the device increases, it affects them minimally. Unlike the BJTs, when we say that if there is thermal excitation, then more electrons and holes movement will take place, and the system may no longer give exactly what it's supposed to give. So thermal stability is a very good characteristic of field effect transistors. Now, what are the few applications of these field effect transistors? As we go on, we will also see the industrial applications of it. The first one is that the amplifiers, they serve as voltage amplifiers at the radio frequency range, and at that range, low noise is of importance. So the FETs serve as voltage amplifiers in the radio frequency and low noise applications. Junction field effect are used for that. Then they have high input impedance buffers and used in amplifiers where such is required. Also, they are applied in switching circuits. These MOSFETs are widely used in logic gates, in microprocessors, and in power electronics devices. In analog circuits, they are used as variable resistors, mixers, oscillators, and modulators. Then, in power electronics, they are used in switch mode power supplies, that is SMPS, motor drivers, and inverters. So, the most important place they find use is in radio frequency and microwave applications, where MOSFETs and gallium arsenide field effect transistors are the key transistors in use for these high-frequency circuits. They are also used as microwave amplifiers. We say that their high-frequency capabilities make them ideal for microwave applications, and in radar systems, MOSFETs are essential components in the high-frequency radar technology. Of course, in your cell phones, they are found for high-speed signal processing and used also extensively in satellite communications, because satellite communications are based on radio frequency and microwave devices. So you can see from what we have said that the field effect transistors have advantages over bipolar junction transistors. And the first thing is they have very high input impedance. Now, when we say that a system or a device has high input impedance, the meaning is that, one, they have minimal loading effect. A high input impedance means that the device draws very little current from the source. This prevents the source signal from being weakened or distorted. Say, for example, if you have a digital voltmeter DVM with high input impedance. When you use it to measure something, it will not disturb the circuit it is measuring. It will not draw more current to operate. It will not distort the signal. So the signal you use it to measure will be exactly the value of the signal you are measuring, because it does not draw its own current from the source you are measuring what is there. So say minimal loading effect is the key advantage of any device having high input impedance. The second one is better signal integrity. The source delivers its full voltage to the input rather than being divided down by a low impedance load. This ensures that the voltage signal is preserved accurately. That is, the voltage you're measuring is what it is. Have better signal integrity. The third one is that you improve the interfacing between stages. For example, in a multi-staged circuit, let's say in radio circuits where you have the RF amplifier, the IF amplifier, the mixer amplifier, there are different stages. If you have high impedance input in all these stages, then each next stage will not require or does not load down the previous stage. It will be just like a seamless maximum power transfer from one stage of the amplifier to the next stage if the stages have high input impedance. So it improves the interfacing between the different stages, more especially in your radio communication systems where you have multiple stage amplifiers. And of course, by doing so, it has high energy efficiency. So, since the device consumes very little input current, it wastes less power from the signal source. So it manages its energy. Like we said, in summary, in contrast, if the input impedance is low, it will draw more current from the source. This can cause voltage drops, distortions, and loading effects, thereby making the circuit less accurate and inefficient. So another, advantage of this is, like we have seen, low power consumption. We said better thermal stability and less noise. But everything with advantage has a disadvantage. MOSFETs are sensitive to static charges. That is, if you have magnetic charges around it, it will affect it. And when you talk of gain, if you are using it to the transistor to achieve gain, then BJTs perform better in gain multiplication for your signal. Thank you for listening. Subscribe to my YouTube channel for more lectures on electronics, computer engineering, and telecommunications. Drop your comments in the comment section, and your questions, if any, can be answered. Thank you.